Hi everyone, welcome to Mr. Naik Math. By the end of this video, you will learn how to solve a linear system in two equations and two unknowns, as well as how to determine the number of solutions that any given system of equations could have. Consider the following equation. 3x plus 1 equals 7. This is a linear equation in one unknown. What is the unknown? The unknown is x. From elementary algebra, we should know how to solve this equation. For instance, if we subtract 1 from both sides, we get 3x equals 6. And now dividing 3 on both sides by 3, we should get x equals 2. Now 2 is what is known as the solution to the equation. Just going to write that down. Solution. Now I want you to recall what a solution means. A solution means the value of the variable that satisfies the equation. We can always check if x equals 2 is a solution to the equation by plugging it back into the original equation. For example, to check, we can say that, okay, 3x plus 1 equals 7. Let's check if x equals 2 works. 3 times 2 plus 1 equals 7. 3 times 2 is 6, 6 plus 1 is 7, and we have 7 equals 7. This works. But another value of the variable, for example x equals 5, may not satisfy this equation. To check if 5 satisfies, let's just plug it into the equation. So 3 times 5 plus 1 equals 7. We want to see if this works. 3 times 5 is 15, 15 plus 1 is 16, and 16 is not equal to 7. And therefore, x equals 5 is not a solution. Graphically, we can represent the solution on the x-axis number line. Our solution is x equals 2, so I'm going to mark that point on the number line. Now this is the only value on the number line that is going to satisfy this equation. X equals 5, as we checked, does not satisfy the equation. So the solution is represented by just a point on the number line. Consider the case with one equation and two unknowns. Let's try to think of a possible solution to this equation. Notice that since there are two variables, we might want to fix one of the variables to have a particular value so that we can find the other variable. For example, let us fix y equals 2. Now if y equals 2, we have 2 times x minus 3 times 2 equals 12. This gives us 2x minus 6 equals 12. Adding 6 on both sides, we have 2x equals 18 and x equals 9. Therefore, we have a solution in an ordered pair form, x comma y equals 9 comma 2. This means that when x is 9, y is 2. But this is just one of the solutions. And we got this because we fixed y equals 2. Let's say we had fixed y equals some other number, y equals 0. Now what happens? We have 2x minus 3 times 0 equals 12, which gives us 3 times 0 is just 0, and so we have 2x equals 12, and so x equals 6. And so we have another solution to this equation, which is x comma y equals 6 comma 0. You might say, hey, there are two unknowns, so you might have two solutions, but we can find one more solution. This time let's try to fix x to 0. Now let's try to find the value of y. We have 2 times 0 minus 3 times y equals 12. We should get y equals negative 4. And so this time the solution is xy equals 0, negative 4. In fact, an equation like this with one equation and two unknowns, where the number of unknowns exceeds the number of equations, this is going to have an infinite number of solutions. We only found 3 of the infinite number of solutions, namely 9, 2, 6, 0, and 0, negative 4. But there is an infinite number. Now you might say, infinite number of solutions. How do we represent these infinite solutions on a graph? In fact, we can graph the number of solutions, the infinite number of solutions. Let's first try to graph this equation. In the previous step, we actually calculated some coordinates that might lie on this graph. For instance, 6, 0 and 0, 4, these are my x and y intercepts. So let me just graph them quickly. You can see that these are the points that lie on the graph. Now all we need to do is connect these 2 points with a straight line. And this is our lovely looking graph. Let's just quickly label the graph. 2x minus 3y equals 12. Now the 2 solutions that we found in the previous step clearly lie on the graph. But what about the other one? Does that one also lie on this graph? 9, 2? Well, let's find out. If this is 6, then this is 9 and this is 2. And lo and behold, we have 9, 2 also lying on this graph. Every other point that lies on this graph is also a solution to this equation. For example, if I look at this point looks like 3, 2. Let's check if 3, 2 is indeed a solution to this equation. Plugging in 3 into x and -2 into y, we have 2 times 3 minus 3 times -2 equals 12. So 2 times 3 is 6, and -3 times -2 is also 6. 6 plus 6 equals 12, and we have 12 equals 12. Left hand side equals right hand side, and therefore 3, -2 is a solution of this equation. Now, I said that there were an infinite number of solutions. This is because of the fact that there is an infinite number of points on this line. For example, some of the points may not even lie on a convenient point where we can read the coordinates, like this point. This is a solution, whatever the coordinates are. X, y, whatever, something, something. And then this point also is a solution. And same with this point, same with this point. And in all, there is an infinite number of solutions. So to conclude this section, we can write down that there is an infinite number of solutions. And all these solutions are in the form x, y. Consider the following situation in which we have 2 equations and 2 unknowns. The 2 unknowns here are x and y, and this type of situation is called a linear system. There are 2 methods to solve a linear system like this: elimination and substitution. We're going to look at substitution first. To solve a system by substitution, we have to pick any one of the equations and isolate one of the variables. It's a good idea to name the equations that we are working with. So I'm going to name this equation A and this one B. And let's say I want to pick equation A and I want to isolate the variable y. So from A, we can go 3x plus 4y equals -2. Now to isolate for y, I need to move the 3x on the other side, subtracting 3x from both sides. We have 4y equals -2 minus 3x. And solving for y, we have y equals -2 minus 3x over 4. What I did is divide both sides of this equation by 4. This is the end of step 1. In step 2, we plug in this value of y into the other equation. In our case, the other equation is equation B. So we're going to write substituting in B. Remember what B was? B was 2x plus 3y equals -1. We're going to substitute this value of y into B, into this. So what do we get? We get 2x plus 3 times -2 minus 3x over 4 equals -1. Even though this equation looks a bit complicated, it is still an equation in one unknown. Notice that we have one equation in one unknown, and this can be solved. That's going to be our step 3. The variable in this situation is x, and so let's rewrite the equation. 2x plus 3 times negative 2 minus 3x all over 4 equals negative 1. Now I don't like fractions, so I'm just going to get rid of this fraction by multiplying the entire equation by 4. I'm going to multiply this term by 4, this term by 4, and this term by 4. So what do I get here? I get 4 times 2x, which is 8x, plus over here the 4 and 4 divide out, and we have 3 times negative 2 minus 3x equals negative 1 times 4 is negative 4. Our goal, remember, is to solve for this x, but x over here is in 2 places, so we have to expand this bracket out, collecting like terms. 8x minus 9x is negative x, and adding 6 on both sides of the equation, I'm getting negative x equals 2. Multiplying both sides by a negative 1, I'm going to get x equals negative 2. Now this gives us one of the variables that we need for the ordered pair solution. To find the other variable, we simply plug this back into the first step, in which we isolated the other variable, y equals negative 2 minus 3x over 4. Okay, so what is the equation obtained in step 1? That is y equals negative 2 minus 3x over 4. And we're going to plug in our negative 2x value into this x. And this is simply going to give us the value of y. So we have y equals negative 2 minus 3 times negative 2 over 4, which is simply y equals negative 2 plus 6 over 4, which gives us 4 over 4, which is equal to 1. And therefore, the solution to this system of equation, we're going to write that as an ordered pair, negative 2, 1. I highly encourage you to check this solution by plugging these values back into the original equation, which is 3x plus 4y equals negative 2 and 2x plus 3y equals negative 1. Both these values of x and y must satisfy both of these equations. We are now ready to learn method 2, which is elimination. We are going to consider the same system of equations as before and show that we get the same solution. For elimination, it is extremely important that the x and y variables are lined up one below the other. In this case, they have already been lined up, but I'm going to write the step down anyway, just to make sure. You can notice that while I line them up, I have actually spaced them out a bit so that we can perform some manipulations. This brings us to step 2, which is to eliminate one of the variables by multiplying the equations by appropriate numbers. So as it stands, if I add the first equation to the second equation, I cannot eliminate any of the variables. For example, 3x plus 2x gives me 5x and 4y plus 3y gives me 7y. So I need to multiply each equation by a number so that when I add the equations, it can eliminate one of the variables. Let's say I want to eliminate the x. I notice that x has a coefficient of 3 and this x has a coefficient of 2 in the second equation. So I'm going to multiply the first equation by a negative 2. And I'm going to multiply the second equation by a positive 3. Let's see what happens when I multiply each of the terms in both the equations. Once we multiply these numbers, it's best practice to write down the equations again. So I'm rewriting the equations with the numbers multiplied. We have negative 6x minus 8y equals negative 2 times negative 2 is positive 4. And the second equation becomes 6x plus 9y equals negative 3. After this step, we have one of the variables having coefficients of opposite signs. In this case, it is the x. So let's add these equations. add both these equations. Adding a negative 6x to positive 6x, we just get 0. Adding a negative 8y to positive 9y, I get just y. So 0 plus y equals, adding 4 to negative 3, I get 1. 0 plus y equals 1, and therefore we have y equals 1. That's a much faster way than substitution to find one of the variables, but it's also trickier because you have to find an appropriate number that you have to multiply. Now, once you have one of the variables, you can always plug it into any one of the equations and find the other variable. So that brings us to step 3. Let's write that down. So I'm going to pick the first equation, 3x plus 4y equals negative 2. 3x plus 4y equals negative 2. Now I'm going to plug in this y equals 1 into this equation to get 3x plus 4 times 1 equals negative 2. Subtracting 4 from both sides, we have 3x equals negative 6. Dividing both sides by 3, we get x equals negative 2. And we have obtained the same solution to our system of equations, namely the solution is negative 2, 1. X is negative 2 and y is 1. Let's take a look at a graphical representation of our solution. If you remember, the equations that we have were 3x plus 4y equals negative 2 and 2x plus 3y equals negative 1. These two made our system of equations. Now, if I were to graph them, 3x plus 4y equals negative 2 looks like a straight line and it has been graphed in red, and 2x plus 3y equals negative 1 has been graphed in blue. And the solution to the system of equations is in fact our intersection point. This is also the solution to the system of equation. If you remember, it was negative 2 and positive 1 for x and y. Let's consider the fact that a graphical representation of the solution of system of equations was the intersection of two straight lines. This gives us three possibilities when it comes to the number of solutions. So the very first case is the one that we just saw. That is, you have a pair of intersecting straight lines, which looks something like this. This is my x-axis, this is y, and let's say the first equation looks like that, and my second equation looks like this. And the intersecting point, or the point of intersection, is the solution. Both of these lines have different slopes. And if two lines have different slopes, then they're always going to intersect somewhere. And so, in this case, we have only one solution. Let's consider a second possibility where you're given two equations and they represent lines so that the lines never intersect. Another word for these two lines is parallel lines. So this is one line and this is another line. Notice that both of these lines are never going to intersect because they have the same slope. But not only do they have the same slope, they also have different y-intercepts. Let's say the first equation is y equals m1x plus b1, and the second equation is y equals m2x plus b2. Here m1 and m2 are the slopes, as you remember, and b1 and b2 are the y-intercepts. For this situation, we're going to have m1 is equal to m2, but b1 is not equal to b2. So in this case, we have no solution, or zero solutions. Now for case 3, we have to imagine two equations which look very different, but when you graph them on the x and y axes, they have the same graph. So in such a situation, if this is my x and y, let's say my first line looks like this. My second line is also gonna look like this. It's basically gonna coincide with my first line. So in this situation, both lines, of course, since they're the same line, they have to have both the same slope as well as the same y-intercept. And therefore we can say that m1 equals m2 and b1 also equals b2. Now you might ask, how many solutions does this case number 3 have? This reduces to the case where we had one equation and two different unknowns. How many solutions did we have at that time? We had an infinite number of solutions. And it's the same thing over here. We have an infinite number of solutions. Another way to think about this is that both of these lines intersect with each other an infinite number of times. They intersect over here, 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 and everywhere in between those points. To summarize, we first looked at the case where you have one equation and one unknown. This is just a simple linear equation, and the solution can be represented graphically on a number line. Next, we considered one equation and two unknowns, in which case we had an infinite number of solutions in the form x, y. Now we're getting to the main portion of the video, which is about substitution and elimination. These are the two methods that we use to solve a linear system of two equations and two unknowns. Method 1, substitution. Method 2, elimination. Then we also looked at the graphical representation of the system of equations, which corresponds to the intersection point of two straight lines. And finally, we looked at three possibilities for systems of equations. You have case 1, where you have one solution, in which case both lines have different slopes. Case 2, we have no solutions when they have the same slope and different y-intercepts. And case 3 is you have an infinite number of solutions when you have the same slope and the same y-intercept. And that is all you need to know for linear system of equations. Thank you for watching and see you in the next video.